So the next speaker is Dr. Denys Poshyvanyk. Okay. While he's setting up, I'll read out his introduction. So he's a Chancellor Professor and the Graduate Coordinator in the Computer Science Department at William and Mary, where he leads the SEMERU research group. His research interest lies in the area of software engineering, software analytics, evolution and maintenance, program comprehension, and DR for SE and SE for DR. He received numerous Best Paper awards, and he is also the recipient of NSF CAREER Award, his IEEE Fellow, and ACM Distinguished Member. So he's going to give us a talk on the topic of interpretability of the code process of LLMs. So please.
All right, thank you very much for the introduction. So one way to motivate this talk is what I picked up from Satish's presentation was that 20 years ago, we were living in the era of, exciting era of the art of manual feature engineering. Some of us in the room remember that beautiful time, right? Where we actually had to use our domain knowledge to engineer features for machine learning techniques that we were using. And suddenly, with the advent of deep learning, we moved to this new stage of art of automated feature discovery. And the reason why I'm saying art, because we're still doing it, a lot of experimentation. But what I'm trying to do with this talk is I'm trying to move from that art of automated feature discovery to science of automated feature discovery. So probably some of you have seen this famous example. And basically, what this shows you is that we have a classifier that basically tries to classify pictures of women and men faces. And the accuracy of this classifier is actually pretty good. It's like 90%. But if you actually drill down into the different classes of inputs, you will see that classifier is not doing that well on images with darker skin and lighter skin, for example, for men. And then you can only do that if you use some of the segregated metrics. So this is actually a well-known Simpson's paradox. And we can easily find a bunch of examples in software engineering context. Let's say you have your language model, which generating you some code. And let's say aggregated accuracy of the generator is 80%, which is pretty good, right? But then you actually drill down into the classes of the results, and you can see that you have getters, setters, you have some functional programming snippets, and for statements. You actually can see that the model, the performance of the model actually varies depending on the type of the token. And actually, this is pretty important because we in research and pretty much most of the papers that I've seen so far, we like aggregated metrics very much, right? We get additional 5% improvement, and we pat ourselves on the back how great we're doing, but are we actually really drilling down into what is happening in the model and what we can actually attribute that performance results to? So basically, what you're observing here, we have all these confounders, right? Like skin types or code features, and these confounders actually allows us to decompose performance into the meaningful model. So the first observation here is that we are dealing in our experiments, and especially in the era of large language models where we have to do a lot of experimentation, we are dealing with confounding bias. And these aggregated measures offer really partial insight into performance of the models. And most of the time, it can lead to misinterpretation of an apparent relationship between variables of interest. For example, like in this case, if we're trying to understand if bugs in the prompt actually have any impact on the accuracy of the code generation. At the same time, these models are already in practice, as we've heard from multiple talks today. So practitioners need a way to understand how the model is generating these results and whether they can actually trust these results. So let me give you one primitive example of how this can be achieved. So you see here two examples. So basically what this model is trying to do is trying to autocomplete a conf function, right? And we have, in the first case, unreliable prediction because the model here highlights some of the features in the prompt that are responsible for generated snippet, and you can say, well, it's gibberish, right? It's using some things which I didn't have in mind. Whereas in the second case, it's actually highlighting meaningful parts of the prompt which make sense to you, and you say, well, actually, I trust the output of the model a little bit more because I understand why this result is actually being generated. So model understanding actually facilitates debugging, and when it comes to interpretability, model understanding is really critical because interpretability can help us facilitate debugging, detecting bias, vetting models to determine if they're suitable for deployment, to provide more recourse to practitioners who are negatively impacted by predictions, and also asserting if and when to trust the model predictions. So in our work, we actually reside in the class of post hoc methods, right? Our causal approach for causal interpretability is post hoc methods. There is a lot of work which has been done with intrinsic methods, and there are some actual experts in the room. And again, many of those methods are coming from that gold era of canonical machine learning techniques, like rule-based models, shallow decision trees. The beauty there was that interpretability was literally embedded in the model, right? You could get a clear understanding why the model is making that decision just by looking into the rules, right? That's not necessarily the case with large language models, right? So this is where causal inference comes into play. So in our case, causal interpretability, we define it as a post hoc global approach by which neural code models are interpreted or explained from a causal assumption encoded in a structural causal model or a graph. So why causal interpretability? It's a really good mechanism to deal or to try to estimate causal effects. So basically, I'm showing you here a very simple structured causal graph, which has treatments, which in this case, we're trying to understand whether bugs in the prompt have any impact on the generated code, which we're measuring with accuracy measures. But we're trying to estimate this causal effect in the presence of a whole bunch of confounding factors, which we're measuring by computing various code metrics. So we're trying to understand how and whether bugs in the prompt have any impact on the generation accuracy in the presence of some of the features that we care about. And we can actually control some of these confounding factors, reduce the impact on the results, and actually see how that will impact the relationship between treatments and outcomes. So causal inference essentially helps us to control for confounding bias by offering explanation or interpretation into models' output. And essentially, if I had to graph where all this work resides, it's at this intersection of deep learning for software engineering and causal inference, which we call interpretable science of deep learning for software engineering. So let me give you just a little bit more information about causal theory, which was introduced by Judea Pearl. So he defines T as a cause of Y if Y listens to T. And basically, causal inference is a process of estimating causal effect from observational data. So here we have treatment T, we have observed outcome Y, and we're trying to measure this causal effect. So, and why this is important for neural language models? Well, this is why. This is one example of a prompt, and this is generated code for this prompt. And from practitioner's point of view, we may get a really good code blue metric or a really good accuracy metric, and technically you're happy with the outcome. But the problem with this code snippet is that it actually has a data leak. Okay, the private key was actually leaked somewhere from the training data, and that's a problem, right? And ideally, we should be able to identify that. Ideally, we need to understand why exactly we're getting that private key, which exactly parts of the prompt, which exactly keywords or concepts in the prompt actually responsible for generating that data leak, okay? So the way to do that with causal inference is actually to generate mathematical formula like this. And again, I'm not going to show you all the details, but essentially we can formulate this question: how is the generated code Y related to code concepts, tokens, and prompt T? Okay, and for that we actually have mathematical language which can help us generate queries like this. So if you look into Pearl's letter of causation, we have level 1, which is based on observational distributions, and this is what we've been doing in software engineering research for a very long time, right? We've been computing all these correlations. Like in this case, we could answer questions like, how is a generated code Y related to code concepts in prompt T? These are kind of questions that we can answer using these observational distributions. So our approach actually resides in the second level, which is called intervention. And here we're relying on interventional distributions to answer questions like, if we remove URLs from the prompt T, will LLM generate API keys? Or in this case, will it produce this data leakage if we remove certain? So it allows us actually to modify the treatment to see if it has any impact on the observed outcome. There is a third level, counterfactuals, but in this case, it may require a little bit more work like model retraining. So the framework that we came up with is called DECODE, which is a framework for causal interpretability method that aims to make deep learning for software engineering systems in the decision-making process more understandable for practitioners. So there is quite a bit of detail going under the hood. So this whole pipeline consists of 4 main stages. I'll go into details into the first stage. That's a really important one. This is where the analyst has the most impact. This is encoding causal assumptions in the graph, but also there are other steps of the process like formulating causal estimate, computing causal effect, and evaluating robustness of estimated causal effect. So in the modeling step, essentially what we're trying to do, we're trying to encode causal assumptions in the graph. So, and I've showed you this graph before. It's a structured causal model, structured causal graph. And we have here treatments. So this is your proposed software engineering intervention. And if you're trying, for example, to understand if the type of prompt or bugs in the prompt have any impact on the results. And by the way, we had very fruitful discussions with Satish that this is exactly kind of experiments that industry is running these days to understand how these things actually can impact the pipeline, right? So in this case, we're trying to understand if bugs in the prompt have impact on the accuracy, on generation accuracy. This is our treatment. So potential outcome, this could be any metric that you pick. It could be loss, accuracy, token, or any other metric that you design. Also, we have confounders. So these are all the code features that potentially may impact both treatment and the outcome. And of course, we have some exogenous variables that could impact everything. So treatments here could be just some binary treatments, like in the context of program repair, for example, it would be buggy code, fixed code. You could, for example, study impact of commented code, uncommented code, or the treatment could be also linear, like, for example, type of clones. So the potential outcome here could be at the global level. So these are type of things that we typically do in the papers. We compute cross-entropy loss, so accuracy. It could be local. So this is actually something that we do to help explain the performance of the model in terms of programming language concepts that developers understand. So in this case, again, you have a model which is generating some code for that prompt that you see there. And here, instead of just showing you the sequence of tokens and probabilities, we actually aggregate this information in the context of the abstract syntax tree that we built from this generated code to show you how well the model actually does in the context of particular programming language constructs. So instead of just telling you this is 0.8 accuracy value, we're telling you that actually the model is doing pretty well in terms of predicting identifiers, but it's not doing so well when it comes to, for example, predicting blocks or some other programming language constructs. And this is actually quite interesting because we ran a whole bunch of experiments to try to understand how this works. So this is one of those experiments that actually shows you that in this case, we did random masking versus AST-based masking, and we actually didn't find any difference. In other words, AST-based masking surprisingly, because we actually expected it to work much better, because we expected the model to pick up syntactic relationships much better. It did not work as compared just to random masking. In terms of confounders, that could be really anything that you think could have impact on the treatment or the outcome. So in this case, we're just computing metrics that lines of code just to see if size has any impact, complexity, number of expressions, returns, variables, so any other features that you want to engineer and compute and measure as confounders. So this is another cool experiment that we've run, and basically the idea here was to understand if certain type of prompt engineering could have impact on the code generation results. So here we have our control prompts. These are just simple short descriptions, okay? And then we have the first treatment, which includes prompts with a little bit more context. And treatment 2, these are prompts which include multiple interactions. They contain like signatures or some more details about parameters or doc strings, so forth and so on. And an interesting result here is that if you use, for example, metrics like CodeBlue, actually if you use CodeBlue, it will basically tell you that there is not that much difference, okay? So the generated code is pretty much, there is no difference, or there is no impact. Or you use Levenstein distance, you see a little bit of difference, but when you actually compute average treatment effect for Levenstein distance between treatment 1 and your control and treatment 2 and your control, you can clearly see that the prompt with much more context, references to the signatures, doc strings, has actually pretty significant positive average treatment effect. So it means that there is a causal effect between better prompts and generated code, okay? In the presence of all the confounders that we controlled in this experiment. So for the other steps, I'm gonna just quickly skim, but there is a little bit of math involved here, so including graph surgery and other cool things. Then we estimate this causal effect. In our work, we use propensity score matching, but you can use pretty much other things like linear regression or even machine learning in itself. And in the last step, we also need to make sure that our estimated treatment effect is actually correct or valid. So, to do that, we can do other tricks like add unobserved common cases, placebo treatment, or common causes. So again, we've used DoCode in very different contexts for different tasks like program repair, commenting, even tinkering with the model itself with hyperparameters. So one note here is that the only thing that you really need to do is to, as an expert, is to define the structured causal graph. Like for the problem that you're working on, you need to clearly define what your treatments are, what your outcomes are, and what are the confounders that you are controlling for. And again, this is yet another experiment which we ran in the context of different tasks and different models. And this is actually answering the question from that cross-cutting example that I've showed you earlier, to what extent the prediction performance of a given neural code model is affected by the presence of bugs in the prompt. And if you just look at level 1, causal association, you just compute this correlation, it shows you, yeah, bugs actually have impact on the generated code. But when you actually do causal intervention, the results clearly show that there is no, so in other words, the presence or absence of buggy code does not appear to causally influence the prediction performance of our neural code model. So this is a beautiful example where causation is not correlation, okay? Many of us know how many times we fell into this trap before, right? So again, this type of framework allows us to do really many things at global and local levels. It allows us to explain overall behavior. It helps us to detect biases at high level. It helps us vet if the model is suitable for deployment. For local explanation, it explains specific domain of samples, helps to detect biases in the local neighborhood, or helps to vet if individual samples are being generated for the right reasons. Like in this particular case, you can have your local explanation, which will tell you for this particular code output which particular AST-based concepts are predicted well as compared to other concepts. You can get a global view of AST-based performance. Like in this case, we compared several different models across different, for example, data structures, types, and iterative, and it can show you performance of different models with respect to those programming language constructs. This is work in progress. Basically, here we're trying to go one level up beyond just tokens. Here we're trying to work with the concepts which are embedded in the prompts. And the basic idea here is eventually try to get an answer to the data leakage question. So in other words, if that particular prompt is generating the code which contains data leak, we want to answer the question which particular, not just tokens, but which particular concepts are responsible for generating that output. If you read our paper, which has been just accepted in Transactions of Software Engineering after many years of work, it has some guidelines on how to apply framework, but also we point out some of the challenges. And some of the challenges are basically related to proposing new syntax, clustering criteria, and again, there is a lot of interesting engineering work to expand it to other programming languages, programming paradigms, but also collecting data in formulating new pertinent software engineering-based interventions. So one thought that I wanted to leave you with is you've heard a lot about naturalness of software, right? It became a very popular term. But I want to leave you with the thought that software information is not only natural on the sequence, but also exhibits causal properties. And I truly think that intersection between causal inference and deep learning for software engineering or large language models for software engineering is beyond interpretability. It's really the whole new science that must be employed to enhance software data analysis, especially in the context of LLMs where we need to do a large amount of experimentation. All right, that's all. Thank you.
So thank Denys for the wonderful talk. So again, we'll save questions towards the discussion period.